Hello everyone. Today we are going to discuss Semester 3 Mechanical Engineering TWEV Basic Electronics Engineering.
Thank you, Professor Nikita. This subject is the backbone of mechanical engineering and helps students connect theory with real world.
Hello everyone, and welcome. Get ready, because today we're going on an amazing journey. We're going to start with something as simple as a grain of sand and end up with the supercomputers that literally run our modern world. Let's jump right in. I mean, seriously, have you ever stopped and thought about it? How does that small device in your hand do so much? It connects you to your friends, plays games, streams movies. It feels like magic, doesn't it? Well, it's not magic. It's something even more incredible: science.
You see, the whole secret behind your smartphone, and all modern electronics for that matter, is being able to control the flow of electricity, almost like a traffic cop. And our story today starts with one very special, very fundamental material. And that special material is called a semiconductor. Now, think of it like this. A conductor, like copper, is a permanent green light for electricity. An insulator, like rubber, is a permanent red light. A semiconductor, it's the traffic signal itself. It can be told when to stop and when to go. And that control, well, that's where all the magic begins.
Now, a pure semiconductor like silicon is a bit like plain rice. It's okay, but not very interesting. To make it special, we need to add some masala. This process is called doping. We add a tiny amount of an impurity to the pure silicon, and that completely changes how it behaves with electricity.
And depending on the masala we add, we get two different flavors. If we add an impurity that has extra electrons, we create an N-type semiconductor, N for negative, because electrons are negative. But if we add an impurity that is missing an electron, it creates a space, or a hole, and we get a P-type semiconductor, P for positive. So now we have two special materials, one with extra electrons and one with extra holes.
So, just to recap, what's that special masala adding process called? The one that gives a semiconductor its N-type or P-type character?
All right, so now we have our two special materials, our P-type and our N-type. What do you think happens when we bring them together? Well, we create our very first and simplest electronic component.
Yep, it's bad simple. We just join a piece of P-type material to a piece of N-type material, and bam! We have what's called a PN junction, or what we all know as a diode. This is the most basic building block in the world of electronics.
So what does a diode do? Easy. Think of it as a one-way street for electric current. Electricity can flow very easily in one direction, from the P side to the N side. But if it tries to go the other way, no entry. The road is blocked. This simple one-way control is absolutely fundamental.
Okay, so if a diode is like a one-way valve for electricity, in how many directions can the current flow?
From that simple one-way gate, we're now going to take a huge leap forward. We're talking about the invention that completely changed everything, the device that made our modern world possible. Let's talk about the transistor. The name itself actually gives us a big clue about what it does. Transistor is a mix of two words, transfer and resistor. That's its job. It transfers a signal across different resistances, and by doing this, it can perform some really cool tricks. The best analogy is to think of a simple water tap, a null. A very small, tiny twist on the handle can control a massive flow of water, right? A transistor does the exact same thing with electricity. A tiny electrical signal, the twist, can control a much larger flow of current. This is called amplification. So, this amazing little device basically has two main jobs that make it the superstore of electronics. First, like we just saw, it can take a weak signal and make it much stronger. That's amplification. And second, it can act as a super fast switch. It can turn that huge flow of current completely on or completely off, billions of times a second.
So let's remember that. What are those two main jobs that make the transistor the absolute workhorse of all electronics?
Okay, so we've gone from the material to the diode to the mighty transistor. Now what happens when you take a whole bunch of transistors and pack them together into one super useful component? You get the operational amplifier, or as we call it, the op-amp. Seriously, think of this thing as the Swiss Army knife of electronics.
This is what its symbol looks like in a circuit diagram. All you really need to notice are the three main points: two inputs, one marked with a minus, one with a plus, and one single output. Just by connecting other components to these 3 points in different ways, we can make this op-amp do almost anything we want.
For example, in one simple setup, it becomes an inverting amplifier. You put a signal in, and what comes out is a much bigger, much stronger, and upside-down version of that signal. It's a fantastic way to boost things.
But wait, there's more. Change the wiring a little bit, and the very same op-amp becomes a summing amplifier. It's like a mini calculator. It can take 2, 3, or even more signals, add them all up, and give you the total at the output. How cool is that?
And it can get even more clever. With just another small change, this circuit can literally perform calculus for you. It's doing advanced mathematics in real time. This just goes to show you how incredibly powerful and flexible one little op-amp can be.
So if a single op-amp can be made to amplify, add things up, and even do complex math like integration, what's the one word that really describes it best?
Okay, let's just pause for a second and look back at the incredible path we've just walked. We've gone from a simple, basic element all the way to a complex, intelligent circuit.
Remember how it all started? With sand, which we purify into silicon. Then we doped it to create our P-type and N-type materials. We joined those two to make a diode, our one-way street. Then we layered them to build a transistor, our amazing amplifier and switch. And finally, we packed many transistors together to create the op-amp, our electronic Swiss Army knife. You see, each step builds perfectly on the one before it.
And listen, this is why all of this is so important. What you're learning here isn't just to pass an exam. You are learning the language of the future. This is the alphabet that's used to build everything from artificial intelligence to the rockets that go to Mars. Every single piece of future technology will be built on these exact principles. You now know the language. The only real question left is, what are you going to build with it?